Yeah, thank you for the invitation to speak, even though I'm not really a probabilist. What I'm more interested in things like that, right? Navier-Stokes equations, and okay, is the existence and uniqueness of solutions, right? And not to go into too much details. So there is a lot. So this equation, okay, models motion of fluids, right? And basically, second law of Newton, U depends on x and t, right? There's a velocity of fluid at position x time t. P is the pressure. This is viscous term. This comes from material derivative transport term. Okay, and this is incompressibility, so incompressible fluid. And of course, we have initial condition. And so we want to see whether solutions exist, and we want, since there is no forcing, okay, body force is 0, we expect solution to exist for all time, especially if initial data is nice, right? Nothing bad happens to fluids, viscous fluids if we don't really stir them, right? So one of the big problems is that we cannot prove it, right? In dimension 3, we cannot prove that this equation has a unique smooth solution that exists for all time, globally in time. The problem is, okay, so the typical analytical arguments, okay, approximation schemes or fixed points, they either lead to local in time existence of smooth solution or global existence and uniqueness for small initial data. And this is kind of a curse of all fixed point type of techniques, because we need some compactness, and so we have to restrict some things, right? Now, what we can prove, global existence of weak solutions, and okay, there are various forms of weak solutions. And why are these solutions weak solutions? It's because in approximating scheme, we can control some things that allow us to pass to the limit, let's say, in some weak topology, as opposed to a strong limit, and so we can only prove existence of some limit points that satisfy equation in some weak sense, without going too much into details. Now, what is the problem with weak solutions? We don't know whether these weak solutions are unique. So let's say from the standpoint of just, okay, PDE well-posedness, again, this is kind of an open question. Although for the weak solutions that are not kind of Lerey-Hov, so Lerey-Hov solutions are kind of some, it's sort of, if you think about it, that they are weak solutions that that maintain some physicality to it. So they satisfy like energy inequality. But weak solutions in general may not satisfy any kind of energy balance. And in fact, there are some recent results that weak solutions that are not Lerey-Hov may not be unique, right? So the notion of weak solution might be just not physical. Okay, so of course, open problem for us are existence and uniqueness. Can we of global solution, global in time solution? Can I for arbitrary large initial data? Can I devise a functional setting where I can prove existence of global solutions and existence and uniqueness for arbitrary initial data? And then perhaps more importantly from, let's say, physical standpoint, can we prove that smooth solutions that we know exist locally in time do not blow up? Okay, and so this is like the $1 million question, literally, you know. So, so why can't we prove this? And the reason is that, okay, so the reason is basically scaling, right? Because if I want to prove existence of strong solutions or regular solutions, so regular means smooth, okay, for lack of, precision. So, so if we want to prove regular solution, we need to control some higher norms, right? So norms that require more slightly more smoothness to prove that, like let's say, our approximation schemes converge in some strong topology. Now, we can only control weaker norms. These are, the double norm is just L2 norm of a solution, right? So this comes from equation. I can control it a priori, and hence I can show that there are some weak limits, basically. Okay, I control some other could control globally some other things, but okay, this is the most famous one, and this is basically H1 norm, Sobolev H1 norm. And then regarding small initial data, why we can prove existence of small initial. So if we have like some kind of condition on the initial, like smallness condition on initial data, and there are many of those type of conditions in many different functional settings. So this is just one of them because okay, I use the L2 and the H1 norm basically. So if initial data are small enough, then I can show that there exist unique global solutions, and that they just come from the fact that okay, if I try to approximate, if I try to see what happens with the nonlinearity of my equation, that's back here, right? So this part corresponds to nonlinearity. So if I want to control it, I have to use some worst case bounds that are sharp, but the natural scaling of equation will make this bound behave in a very special way, and so because I'm in dimension 3 L2 norm, if I see so what is the scaling? So if I have a solution, let's say in the whole R3, and I rescale that solution like that, then I get another solution, right? So it's a symmetry that is embedded in the equation. And so if I look at the norms that the quantities that I can control globally, like L2 norm, I see, okay, if I rescale it by lambda, I see 1 over lambda. So if lambda goes to infinity, right, if I like zoom up to very small scale, this goes down, right? Now, if I see, so this type of quantities are called subcritical with respect to this particular scaling. Now, if I look at the thing that I actually want to control, it's supercritical. So when I rescale it, I have an extra lambda coming in, and then okay, if I zoom to rescale to very very small scales, any kind of like bad behavior gets amplified basically. And then, okay, but if I see the things that lead me, like typical small initial data type of statement, if I rescale these things here, I don't get any lambda, so basically it's conserved. It's invariant with respect to scaling, and so such quantities are called critical. And so any kind of sharp inequalities that I get, like from Sobolev type of inequality, they are all critical with respect to scaling. They cannot break it. And so I will never be able to control this type of norm, supercritical norm, just by using worst case scenario. So I actually have to look at the dynamics and see why would solutions stay away from, let's say, from some kind of extremal type of vector fields, right? That would saturate some inequality, would saturate the worst case bound on the nonlinearity. And it should happen in some average sense also, right? It could come there for like a little while, but it cannot stay in that region for a long time. And this type of dynamical estimates, it's kind of beyond us for now. Like for PDEs, nonlinear PDEs like that, and so that's why this is $1 million question, right? So it's in a nutshell. There's like more things that one might say. And so the question is, can we break this scaling? How can we break this? So we want to understand this scaling, and perhaps the most natural thing to do is to start with like scaling invariant solutions, right? And it's idea that goes back to Leray, who first proved existence of weak type solutions. They call they named after him after. So in like 30s. So we look. If solution preserves or invariant with this type of scaling, in the Fourier space, it would look like that, right? And why might we want to look in Fourier space? It's a natural thing to look at what happens with like scales, right? So how does energy of a solution kind of moves between scales? And so perhaps understanding these solutions, maybe this type of solutions in might help us to see what happens with the scaling, right? And okay, so what do we do? Okay, so we want to write Navier-Stokes basically in the Fourier space, right? This is a kind of variation of constant formulation. Okay, so this part comes from the fact that I have a Laplacian. So this is xi squared is a symbol for Laplacian. And then this part comes from nonlinearity, right? So we think of nonlinearity as a forcing in a linear equation, and that's the variation of constants, basically, right? And now this part, okay, this type of product comes from the structure, U dot grad U structure. So this xi here comes from the fact that I have derivative, right? And then, okay, there is some constant, and then, okay, products will become convolution types, and then there are some projections, right? Because I have a divergence-free vector field, the pressure disappears. And so this O dot product, this type of projection is okay. It's in the Fourier. It's a sort of a non-local type of thing. It's exactly projection on the divergence-free vector field. This condition xi dot u hat of xi equals 0 is exactly the condition that divergence of u equals 0. And okay, this type of condition I have to impose because I want my solution to be real valued as opposed to complex valued. And then, okay, so this product, since I scaled here out xi, this product, these projections here really depend on the direction of xi. Okay, so now I look at this equation, and let's suppose I have a scaling invariant solution. So I have something like that, right? And so now, I can plug any lambda here. So let's try lambda equal xi, right? So Leray tried lambda equal t. Lambda squared equals t. Well, lambda squared equals 1 over t. He canceled t. But okay, and not in Fourier, but in physics. But anyways, so we get this scaling. So we rescale this scaling, and this is pretty much what we get, right? And so now my equation is, that's just okay calculations. And then change variables, right? So change variables, okay, this denote this by tau. And then change eta with eta over xi and things like that. So it's just, okay, calculations, and this is what we get, okay? And what is interesting is, okay, so this is kind of nice. You've seen this before, right? This gives us idea of like exponential clock going on somehow, right? So it's nice, but then, okay, this kernel, it turns out to be integrable. So if I scale it, so I can think of this as a probability distribution in space. So now I can view this whole statement as some kind of expectation, calculation of some expectation, and that's kind of the idea that goes. It's not in this setting, in this type of form. But the idea to look at mild formulation in Fourier space and then rescale it somehow and think of the rescaled equation as expectation of something goes back to a long time ago. But okay, in particular for Navier-Stokes, it goes back to Lejeune and Schnitzman's paper in '97. This is what is interesting is that this kernel comes in naturally. Right, it just comes in for scaling. I didn't try to do anything. I just rescaled with respect to scaling that the equation already had, right? And so notice that, okay, so this calculation was done under assumption that the U was self-similar solution, but I don't have to assume this, right? All I did here, I divided by xi. So even if the solution non-self-similar, I can do the same thing and get, okay, equation for non-self-similar solution, and my kernel is this. It's still integrable. So I still can view it as equation in Fourier sort of as an expected value of something. So the only difference between these two is that, okay, here initial data depends on xi, here initial data depends on the direction only. That's the only difference between these two, actually, like maybe from practical standpoint. So okay, so I don't want to carry hats anymore too much, and then also it's not v is not quite u hat, but okay, it's a constant times u hat to make here constant 1, right? So now let's write this equation. So this is basically a representation of a self-similar solution, just rescaled a little bit, of Navier-Stokes equation. Okay. And okay, so now I say, okay, so I view this as expected value of some process x, right? That depends on t, and this tau is we call it similarity horizon. It's a time-like variable here, so we still have dynamic. And so okay, so I'm computing expectation, right? So if I have a process that in distribution looks like that, right? So we have some, okay, so initially it's maybe constant, V0, right? And then this is just O dot, this funny product, right, of two IID copies of itself, just rescaled, right? So if I compute this expectation, this is what I get, right? Now, the time here is exponential 1. W1 follows this distribution, right? And W2 is E minus W1, right? So this is my W1, this is my W2, right? I mean, this the direction comes from it. And so if I compute expected value, that's what I get, right? And then, okay, so what follows? So if I can show that, if I can find such a process, if I can define, if such a process exists, and moreover, its expectation, its first moment is finite, then I can show that it's actually that expectation of this process will produce a solution to this equation. Okay, so the question would be, okay, from a probability standpoint, I traded my problem of finding, okay, maybe fixed point of this mapping or something, to a problem of constructing a process like that. Okay.
It doesn't have a uniqueness. It just exists.
That's cool, right? So this is a mild formulation. I would like to see a self-similar solution in this setting that exists for arbitrary large initial data. That will give me existence for large initial data, for general solution, for mild solution, and that.
But then the question is the resulting thing, how nice it is, right?
That's a second question. Yes, if I want to go to regularity, I have to see what happens if initial data is regular. Can I make it smooth? So for now, I want to see, okay, can I construct the process? So if you want existence as uniqueness, right? So I will have existence. What do I do with uniqueness? That's the second question. Is it a unique process? Indeed. Or maybe there are many processes, but if I take expectation, they all have the same expectation. Who knows? But yeah. So okay. So you kind of can see, like, we've seen trees before, but there are like trees involved, right? So this is kind of like the frequency, let's say, that came from xi. Okay, the direction it branched in two directions, right? W1 and W2. And the time, the similarity horizon gets changed with the, according to the branching. And then, okay, x1 and x2 may branch in their own right? So you have this tree structure, right? And you stop branching. When do you stop branching? When your clock exceeds this similarity horizon, right? So you have this tree, right? So this tree keeps branching, right? So you sort of you produce this IID, family of these time clocks, capital T, right? And you start with tau and with maybe xi, right, or direction of xi. And then you produce W1, so you run your clock. If the clock doesn't tick, right, then this Xi branches in W1 and W2. And W1 has this distribution, right? And W2 is the other one, right? And the process starts anew, right? And as soon as my clock ticks, right, my branching stops, and I would assign this initial condition to that branching, right? Evaluated there. So, and then what do I do with my initial conditions? I would make up a big O dot product along the tree. So, for example, if this branch ended, this X must be this. There is no other way, right? That would be true recursive relation for X, right? So, what is explosion in this setting? Explosion is, okay, is this tree finite? Almost surely. Right? If I can prove that this tree is finite almost surely, I will answer uniqueness question, right? Then this must be X, right? There is no other way of constructing X that satisfies that. Now there is an argument that is rigorous argument about uniqueness in the case of no explosion that goes back to Lejeune and Schnitzman. But okay, do we have this no explosion? So again, explosion. So let's look at this. Now, what else do I want to say? If there is no explosion, I don't have to worry about constructing X of t. So I can just follow the tree and I get my X of t. Right? If I have explosion, then I don't know whether X exists at all. Right? So so this explosion actually affects the uniqueness and existence, both of them. Oh, what is my time? Okay. So, so let's look. Okay, how do we understand the explosion? So we notice that, okay, if I take a vertex, right? So this vertex survives if the clock didn't tick, and then okay, I unravel what this means. And okay, as long as this is not negative, right? So this is kind of a so let's call this S. Let's say takes a minimum of all these of all this. By the way, so the notation. So B is a vertex, right? So it's like a sequences of ones and twos, right? Left, right. And K means that okay, it's so I cut my sequence in the first K components. Okay, so that it makes sense, right? So so this kind of represents times of the branch of length K that comes from like some path that has K generations, right? And so I take infimum over all this path, and I take and go to infinity. This is kind of this is like sort of time-like, so time length of a path, if you will. And then okay, you take if I take limit of this, I get the shortest path of the tree. If I continued it, right? So I can continue branching. Only my clocks were all okay, you know. My clocks ticked, but I could continue producing these W's, right? So okay, so I get this. So if this is less than infinity, then I have explosion, right? Then if my tau is bigger than this, then it means that there is a branch that didn't reach time tau. There is a branch. There is at least one branch. Well, at least one. There are branches that keep branching without end. So I have infinite tree in that case. Right? If tau is bigger than that, so no global global solution at that point becomes a questionable thing, right? So that's why we call this event explosion event, right? So it's not explosion, but it's event independent on tau. By the way, this S is actually independent, is rotation invariant. So the distribution of S doesn't really depend on Xi. So this is sort of, we call this shortest path, and this is explosion event. Any questions so far? So I want to see, okay, what is the probability of this event happening, right? And okay, so let's perhaps look at a very, very simplified case, right? Let's simplify everything, right? So let's ignore. Let's suppose. So here we have a sort of probability kernel. Let's suppose it's like Dirac delta. Okay. Notice, by the way, notice that just like by this tree definition, right? So if this H, right, this kernel, okay, we know what it is, but if that kernel prefers big frequencies, if W1 and each time the frequency branches into frequencies, the children have big magnitude, so if the branch survives, right, it tends to generate bigger taus, right? Bigger time horizon, and so you will have less chances for clocks to tick, right? So big frequencies, big W's mean more branchings and more chance for explosion, right? So more explosion becomes more probable, right? So so you can think of this square root of lambda is the square root of alpha is the size of a frequency, right? Maybe some kind of average size of a frequency. I don't care what this lambda is for a moment. So okay, so it's just okay. I'm thinking that h1, so eta 1, I don't really care about its direction. I just think that the two children would have about the same size, okay, square root of lambda, and I ignore the rotation. I just look at the magnitude, and this is basically what I get. It's like very simplified baby problem for Navier-Stokes, right? So I kind of strip down everything. Okay, so this is what I get. Okay, in differential form we get equation like that. When lambda alpha equals 1, right, it's logistic or Riccati type equation, right? We know how to solve it, right? When alpha equals 0, it's very easy to solve, right? But otherwise, we're interested what happens in particular when alpha bigger than 1, right? We have more branchings, right? When alpha less than 1, we have less, right? And so we want to see what happens with this equation as a kind of motivator for what would we expect for Navier-Stokes. And so okay, so what's so let's see. Okay, so we can write solution variable for our solution process for this equation. Okay, so again we notice that we don't have to worry about frequencies. They're all fixed at square root of alpha, right? We only have clocks ticking. Right, and then the frequency each time you get the children of the same size, right? And so okay, so I get this tree, right? So it's exactly like Navier. I mean, it's a similar idea as Navier-Stokes tree, only much simpler, right? And okay, but okay, what we don't have to worry about a dot product if this tree ends. Okay, I just have to count how many branches do I have in the tree, and my solution will be initial data to that number of branches. Here, V0 would be expectation of this X0. Why do we call this inherited property? Okay, for lack of a better name, right? We have inherited events, in the book, right? So if I have an inherited event, by the way, okay, so what would be inherited event? No explosion would be inherited event, right? So if I have a no explosion for this tree, then each of these sub-branches will have no explosion, right? So this would be inherited event. And if I want to compute probabilities, if I want to compute expectation of inherited event, I will have to consider this process an indicator of that event. It's a constant process, and it will exactly satisfy this equation. So it's kind of, okay, maybe generalization of, if you will, to time-dependent process. Right, okay, so so we have like shortest path, we have longest path, right? So, and then we have this explosion event, and this is hyper-explosion event. So if L is less than infinity, it means that, that if tau is bigger than this L, then none of the branches ended. This tree is like full tree, continues to infinity, nothing reached, nothing ended, right? Okay, so now I have, so as I said, if S equals infinity, that's inherited. If L less than infinity, that's inherited as event, right? Now, what also inherit, like time-dependent processes, indicator that S bigger than tau is inherited. Because if L is bigger than tau and I rescale it to the children, then the children, like it says, the children will have their s bigger than their tau, right? And their children for each L will be less than their corresponding tau, right? So this process should be tau here, but okay. So now, but there is no problem with expectations here. They have finite expectations. So these are all solutions, automatically solutions of my alpha Riccati equation. Of course, they correspond to very specific initial data, either 0 or 1, right? Now, if we have no explosion, some of this will coincide, right? So like, but okay. So in the case, I don't know, yeah, time, wow. In the case alpha less than 1, right? Alpha in 0, 1, there is no explosion, and it's very easy to see. So the number of branches is, bounded by Yule process. So doesn't explode. So in this case, so this is in the case when we produce children that are in magnitude less than their parents, right? And so in that case, we have like existence and uniqueness theory for large arbitrary large initial data. But we have this kind of asymptotics. We can actually say that so that the solution variable is this. It has to be this, and we can. Why do we know that it's finite? Even expectation is finite even when we 0 bigger than 1, because we can estimate this probability. Probability that the number of branches equals exactly n. So I can compute it, and so find that it's finite. And so I have a unique solution. The fact that it goes to infinity from the standpoint of Navier-Stokes, it means that I have lack of Hadamard well-posedness for this problem, because my natural setting would be L infinity type of setting. Anyway, so we have a special cases here where we can compute this distributions exactly, right? And we recover our alpha equals 0 equation. Alpha equals 1, just usual logistic solution just from probabilities. Alpha equal 1/2, it's perhaps a case where which student in basic ODE class would not be able to solve because it's not ODE, but okay, we can do it, right? So in case alpha equals 1 is different, right? So case alpha equals 1, we actually have explosion. And okay, so there is an argument why it has explosion, because we can if we choose a path. So if we choose a path such that at each vertex you go with the biggest descendant, right? Descendant of the biggest size. If that path has finite length, then the whole thing exploding. For alpha Riccati, we have alpha, right? So when alpha bigger than 1, we have paths of finite length with non-zero probability, so it's exploding. And so, okay, so, but in fact, it's more than that. Alpha Riccati cascade is, in fact, hyper-exploding. So not just probability that S less than infinity, probability that the longest path less than infinity is 1, right? And so if I pick tau bigger than L, let's say, somehow, if it happens, then none of the branches ended, right? And this happens. Now, how do we do this? How do we construct solutions in the case when we have exploding cascades? Well, we do iterations, right? Instead of writing solution variable, we just iterate some x0, basically. And when we iterate some x0, like if expectations make sense, then expectation satisfies this Picard type of thing. And perhaps the most natural one is to choose x0 equals 0, right? The initial iteration x0 equals 0. And in that case, okay, I can actually write what is my so my iterations converge to something like that, where n of t is number of branches again. Should be tau, right? Okay, have some t's randomly. But okay, so nevertheless, like for small initial data, I can prove we can prove existence and uniqueness. So any solution, but it has to be in the class of solutions oh no, this is the different theorem, right? So if this is less than infinity, okay, it's a solution, fine, but it's also the smallest possible solutions among solutions, right? And then we have this theorem, basically the theorem that if V0 is less than this, right? So it's basically small initial data result, right? You have the final expectation, so you have existence of solution. But if V0 is bigger than then you have blow up in finite time, right? So for big enough initial data, I guarantee to blow up any solution, but there are no global solutions in that case. Okay, and this is the existence and uniqueness. So if I choose initial data less than 1, then the minimal solution will be unique solution in the class of solutions with that keep being less than 1. Okay, and then what? Okay, so there is now what happens? What happens if I don't remove this restriction? Even if for initial data in 0, 1, I have at least 2 solutions. So all I have to do is to initialize with x0 equals 1, and so I have non-uniqueness for arbitrary small initial data. And so what is the reason? The reason is that I am free to choose this x0 completely independent of initial data. As long as I can prove convergence, I produce another solution. So this is potentially highly non-unique. And okay, we can do it, of course, for if we we have also non-uniqueness for initial data, for which we can prove existence. So we can produce solutions. And we also can incorporate initializations that are random themselves, random variables themselves. And in that case, we use martingale type of techniques to get convergence. And we recover we would recover other solutions like that. Okay, so this is kind of a picture of the sort of what we can prove. So it's just studying cascades, right? So all of these results are proven just using probabilistic methods, right? So this is alpha, this is U0, right? In this region, we have existence and uniqueness. So this is all about global solution, existence and uniqueness of global solution. Here, right? If initial data, so this is result of small alpha, right? For small alpha, everything is nice. Now for big alpha, I start having what? I start having finite time blow up. Now in this region, I don't know, right? So these 2 lines just didn't meet for me. And they don't meet even if I try, I don't get any better if I tried analytical techniques. But there are local solutions, although, there is a... local solutions also non-unique, by the way. So and then there is this region here. So this region when initial data is strictly less than 1, I have existence, of course, and I have non-uniqueness, but in the class of solutions that are less than 1. And here I have existence and non-uniqueness for sure, right? So what we think is that for Navier-Stokes, what happens is for Navier-Stokes cascade is exploding. And this is kind of a very recent result. I mean, one has to use nice properties of this kind of distribution that comes from scaling, right? And it's exploding, but of course, it's the question is more complicated than that. So we can, for example, we can definitely recover existence and well, this is exploding and proof, probably not for today, but we can recover the theorem exactly the same as for alpha Riccati, that if in the class of initial data that is less than 1, I have existence and uniqueness. Now, okay, so we suspect that solutions, these mild solutions of Navier-Stokes are not unique because of explosion. But okay, so and this type of iterative procedure, when we use arbitrary initialization, is we hope to use it somehow to produce non-unique solutions for different initializations U0. The problem is this O-dot product, right? So O-dot product has projections, and it has and projections have cancellations, right? produce cancellation. So you have basically data, right? You say your initialization get projected over and over again on random directions. If you have explosion, there are like these products becomes bigger and bigger, right? And so you have a lot of projections of the same thing basically on random directions. That has a chance to kill any kind of big initial data type of thing, in any kind of problem with big initial data. So one may actually, so if there is enough cancellation, one may actually be able to prove existence for large initial data and also uniqueness. Because maybe it doesn't matter what you put in, that thing actually acts as if you put 0 as your initialization, right, or repeated. And on the other hand, if we can produce initial data, let's say we can produce some kind of vector field to plug into branches that didn't end, that don't cancel with respect to this O dot product, then we will produce non-unique solution. And non-unique solutions is kind of like there are other things, right? So there is a potential connection to turbulence, right? Because it's naturally tells you how frequencies are distributed, right? In most cases. So, but that is kind of a future work. I think I'm sort of out of time, maybe, right? So I should end here.
Any questions?
How do you know these things are supposed to produce strong solutions in Navier-Stokes?
I didn't say strong. They're mild solutions. So they're mild solutions like, okay, Kato studies. So these are legitimate solutions. These are better than weak solutions.
So they would be unique if they existed?
Maybe not. If we can exploit explosion and produce different solutions, maybe this would be an instance where you have mild solutions that are not unique, just like for alpha Riccati. So in fact, in the like Navier-Stokes community, there is more and more skepticism about uniqueness of solutions for Navier-Stokes, and so this is a result in that type of direction. So there is if we can, but then this O dot product is the key. Okay. But what I like about this approach is very dynamical. Right, so there is dynamics involved here.
Any other questions or comments? Trying to mention one other, that an explosion. So Enrique Angel, back some 20-something years ago, motivated by similar considerations, asked a question on explosions, and I have a paper with Robin Pimentel on that. I won't give any more details, but if anyone is interested, happy to discuss more. Any other comments or questions to Radu before we conclude? Okay, if not, let's thank all of today's speakers.